Uh, all right, so I know that earlier this week you learned about SN1 and SN2 reactions. And today we're going to talk about their cousins, which are E1 and E2 reactions. And I included a meme, which says organic chemistry is 1-emo 2-hurting dimethyl ethyl Pucci, which is pretty funny, I think. Anyway, let's keep going. Oh, come on. So what do we use E1 reactions for? So here's the general scheme for E1 reactions. First, you start with a simple alkane or a substituted alkane, it doesn't really matter, with a leaving group. So in this case, I have Br as a leaving group. So through an E1 reaction, we're going to get rid of the leaving group and get rid of one of the hydrogens on the alkane and make a double bond. So E1 reactions are really just to help us go to alkene from an alkane. So next thing we're going to talk about is the mechanism. We're going to cover a lot of things today, so I'm going a little bit fast. All right, so for an E1 reaction, sorry, somebody wanted to ask a question? No? All right, I'm going to keep going. For an E1 reaction, the first thing that happens is the departure of the leaving group. So the leaving group just decides to leave on its own, which generates a carbocation. And then the second step would be that leaving group comes back to grab a hydrogen. And then we form our double bond and an acid as a side product. So E1 reaction mechanism seems very straightforward, and it has some resemblance to the SN1 reaction because the first step for an SN1 reaction is also the departure of a leaving group. However, the difference is that in E1 reaction, your leaving group comes back to grab a proton, whereas for an SN1 reaction, a different nucleophile would come in and attach itself to the carbocation. So for an E1 reaction, we can get multiple products. This product I just drew was the most obvious one because I highlighted this hydrogen in my schemes. We got to still pay attention to other potential products, and it's all about beta hydrogens. So I bet some of you want to ask, what are beta hydrogens? Well, let's look at this picture here. See the carbon that's directly attached to the leaving group? That carbon is an alpha carbon. And if we start from the alpha carbon and go one carbon over, that carbon would be a beta carbon. And in this molecule, there are 3 beta carbons. And I hope you can see my cursor because I'm pointing at them right now. So hydrogens attached to beta carbons are called beta hydrogens. And when we do an elimination reaction, what we eliminate is beta hydrogen. And if a molecule has more than one beta hydrogen, what's going to happen is that we're going to get multiple products. So, question for all of you. How many beta hydrogens are there in this molecule that I've been using as the example? I'll give you a little bit of time and imagine drawing out all the hydrogens and identifying all the beta hydrogens.
Is there 7?
Or 7? That sounds like a great answer. So can you tell me where the 6 missing hydrogens are?
They're on the
That's
beta carbons over there.
There are 2 beta carbons over here, and each beta carbon has how many hydrogens?
3.
Each has 3, so we have 6 plus this one over here. Wonderful. So how about this one? This one, I did not give you any hydrogen. So you got to figure out where they are and identify all the beta hydrogens.
I have a quick question.
Yes, absolutely.
How do you identify if something's a beta carbon again? Sorry.
How do you identify beta carbons?
Yeah.
Yes. So let me quickly go back to my earlier slide. So first, we have to identify the alpha carbon. Alpha carbon means the carbon we're interested in, the carbon where the departure of the leaving group happens. So our leaving group is just a heteroatom in this case, which it's bromine, and the bromine is attached to this carbon. Therefore, that carbon is alpha carbon. And one carbon away, we call that carbon beta carbon. And in this case, there are 3 of them. Did I answer your question?
Yes, thank you.
You're welcome. Okay, so here, how many beta carbons do we have?
Is it
9.
Multiple people were talking. Sorry, I didn't catch any of your answers.
Oh, I said 8.
You think there are 8. Can you pinpoint where exactly they are? That's the correct answer, by the way. Congratulations.
So the leaving group would be the Cl. So then,
Yep.
yeah, the attached to it would be the alpha carbon, and then you
Yep.
have 2 methyl carbons coming out of that one, which would be the beta carbons and then the beta hydrogens. So then that'd be 3, 6, and then going to the right of that, you'd have your then yeah, going to the right of that, then you just have like the 2 hydrogens that are attached, like the 2 beta hydrogens.
Mm-hmm.
Yeah.
So I don't know if everybody caught what he said. Basically, here's literally what he meant, but in picture. So there are 2 methyl carbons that are beta carbons, and each methyl carbon has 3 hydrogens attached to it. And then don't forget that if we go to the right, there's also a beta carbon, which is a benzylic carbon. A benzylic carbon means that it's 1 carbon away from a phenyl ring. We call it benzylic position. And the hydrogens attached to this beta carbon, we have 2. So 2 plus 3 is 8. There are 8 potential hydrogens that we could pull away if we wanted to do an E1 reaction. Any questions that we have until this point? No? Okay, I'm gonna keep going. So we can form multiple products. How do we know which product is gonna be the major product and which is gonna be the minor? Well, if we look at the first reaction on here, the E1 reaction happens, and we happen to get rid of this proton over here to the right, and we get a tetra-substituted alkene. By tetra-substituted, I mean that there are 4 non-hydrogen things attached to the carbons that have a double bond between them. Okay, so if we look at the second reaction, instead of removing the hydrogen to the right, I'm going to remove one of the methyl hydrogens. And as a result of that, I'm going to form this alkene, which is disubstituted. By disubstituted, I mean there are 2 things that are not hydrogens on this alkene. So a long time ago, a Russian chemist whose name is something that I'm not even going to try to pronounce, Zaitsev. And I don't even know if that's the right pronunciation, but Zaitsev figured out a rule for figuring out the major product from an E1 reaction. That is, more substituted alkene is more favorable. In other words, more substituted alkene is more stable and would prefer to be formed. So there's more to Zaitsev's rule. So for the major product, we also call the Zaitsev product, it is a thermodynamic product, which means that it is the more stable product. The formation of the thermodynamic product is generally slower and the product is more stable. Whereas the minor product, we call it a Hoffman product, it is kinetic product. That means that the formation of the product is generally faster. However, the product will be less stable. The minor and major products are always in equilibrium. And if you notice, here I drew 2 arrows. The arrow on the left is slightly longer than the arrow on the right, which means what? Does anyone remember this from Gen Chem? Just gonna sit here until somebody talks.
Does that mean like there's more of the major product than the minor product?
You're absolutely right. So the equilibrium lies towards the major product, which means that given enough time, your kinetic products are going to go to the major product. However, if you don't give it enough time, you're going to have different amounts of major and minor products. So that's the Zaitsev rule and major minor products for you. Any questions at this point? All right, I'm gonna keep going. So I know that for SM1, SM2 reactions, you talk about rate limiting steps. And just as a refresher, rate limiting step is the slower step. And for an E1 reaction, which step is the slower step? Well, is it the departure of the leaving group to form the carbocation, or is it elimination of the hydrogen to form the alkene? That's a very important question, because without knowing what the rate limiting step is, you're going to get the wrong rate law. So let's take a guess. Which step is the slower step? And I have a hint for you, which is carbocation is very unstable. And if it can refuse to exist, it will refuse to exist. So let's take a guess. Which step do you think is going to take a very long time?
The leaving group, like leaving and the formation of the carbocation. Because I remember from previous lessons, the more unstable the carbocation, so like primary carbocations have a lower reaction rate. So applying that same concept, carbocation formation is unstable, therefore that would be the rate limiting step. The first.
That is an excellent answer, and I could not have said it better. Thank you, Karina. So just to reiterate what she just told us, carbocations are unstable, which means that to make them, it's going to be very hard. And the leaving group would have to be very determined in order to leave. Once it leaves, we have this carbocation, which really is not very happy. So in order for this carbon to be happier, the elimination of the hydrogen is going to be a very fast step. So the first step would be the rate limiting step. The rate law would accordingly be K times the concentration of the alkane. K is the, what do you call it? Rate constant, and concentration of the alkane is self-explanatory. So any questions at this point? Which order is the reaction? Is it first order? Is it second order? Is it we don't know?
First order.
It is a first order because of what?
Because it has one molecule.
Because it is a unimolecular reaction in the first step. Right, you're absolutely right. The concentration of this reaction determines how fast it goes. So if we have a lot of alkane with a leaving group, this reaction is going to go faster. If we have low concentration, this reaction is going to be very slow. Okay.
I have a question.
Yes.
I understand that it's unimolecular and therefore it's like first order, but why would a higher concentration of alkane make the leaving group more determined to leave? Like, why would, like, if there's less of the initial molecule, why does that make the leaving group less likely to leave? Because the rate would decrease for the reaction, right? If the concentration of the alkane decreases.
Sorry, can you repeat the second part of your question?
Yeah, so since according to this equation, the rate of the reaction decreases as the concentration of alkane decreases.
Mm-hmm.
But why is the BR leaving dependent on how many of those molecules are present?
That is a very good question. I don't think I can give you a one sentence explanation. So why don't we talk about this after this lecture if you have time? If you don't have time, we can schedule a separate meeting to talk about this. All right? Thank you. That's a very good question. Okay, so let's move on. The E1 reaction reactivity is very similar, or pretty much just the same as SN1 reactivity. Tertiary carbocations are going to react faster than secondary carbocations than primary carbocations, decreasing reactivity because the stability of those carbocations decrease as the number of other carbons decrease. Any questions regarding this point that I just made? No, right? Because you already learned about this on Monday. So next we're going to move on to E2 reaction. It is very similar to E1 reaction, except that it is a concerted reaction. So the first thing that happens is that you have the base that comes in to grab the proton. And when the proton leaves, it's not going to take its electrons with it. It's going to dump a pair of electrons between the two carbons, the alpha and beta carbons. And then the alpha carbon would become very upset because now it has 5 bonds. In order to be happy again, the leaving group has to go. So that's the concerted reaction. And in the end, we get a product that's an alkene. So can people guess the rate law for this reaction? It's very similar to the other one that we have. It's just instead of 1 molecule, we have 2 molecules.
Would it be K times the alkane and the concentration of base?
That's absolutely right. We have 2 things involved in this reaction, and the rate law would just be K times concentration of alkane times concentration of the base. All right. So one thing that we have to pay attention to is the conformation of the alkane. The H and Br cannot just be at any random position. The alkane has to have the correct conformation in order for the E2 reaction to happen. That is, that the H and Br have to be pericoplanar. Now, what does that word even mean? Well, it means that they have to be in the same plane, hence the coplane. Here I drew a plane, and the H is in the plane of your computer, and Br is also in the plane of your computer, and the other alkyl groups are coming in and out. They have to be in the same plane, but they also have to be on opposite sides. In order for this reaction to happen, your H and Br has to have to be on different sides of the alpha and beta carbons. So, did somebody say something? No? Okay. So here's, I believe, next slide, I have some practice problems for you guys to see whether or not in those conformations, the E2 elimination reaction can happen. Okay, let's look at the first molecule. Here's a very similar molecule to the one that I just drew. Can E2 reaction take place in this molecule?
No.
No.
No. Multiple people said no. Why is it not okay?
Because they're not pericoplanar. Because they're the Br is on a wedge and the H is on a line.
You're absolutely right. Yes. So the Br is, imagine this molecule in 3D, which I believe you now are capable of doing. The Br is coming out towards you, whereas the H stays in the plane of your computer screen. Therefore, they're not in the same plane, and the molecular orbital are not going to overlap. And for those who are really interested in how molecular orbital plays a role in this, we can talk about this after class. For the scope of this summer course, you don't have to know how exactly that works. But I guess for the actual course, you may learn this. Okay, so that's the first molecule. How about the second one? They're both pointing inside. So I guess that's a good thing.
But they're not on opposite sides, right? Like
You're
even if
not on opposite sides, you're onto something very important. So the H is going back, the Cl is also going back. And those things are kind of cis to each other. In order for an E2 reaction to happen, you have to have them trans to each other. Therefore, this conformation cannot let E2 reaction to happen either. However, we have to remember that for single bonds, they can freely rotate. And if they rotate and reach the ideal conformation, E2 reaction can take place. Okay. All right, I don't know how many slides I have left. This is probably the last one because this lecture is not that difficult. Any questions regarding what I just taught? Because that's all there is to E1, E2, and Zaitsev's rule. So E2 reactions also follow Zaitsev's rule: more substituted, more stable, more favorable. Less substituted, less favorable, less stable. So
I had a question.
Yes.
So is the pericoplanar conformation exclusive to the E2 reaction?
that's a very good question. And the answer is yes. The reason is that for an E1 reaction, you have the leaving group depart from the alpha carbon. And what you have is a trigonal plane. So imagine you have a plane in the plane of your computer screen. And the H could be removed from bottom or top. It doesn't really matter because your leaving group is already gone.
Thank you.
You're welcome.
I have a question.
Yep.
If you could just go back to the last slide, please.
Last slide. This, sorry,
Yeah.
am I still sharing my screen?
Yeah, you still are.
Oh, okay, wonderful, cool.
So, like, how could we change the molecule to make the H and Cl be on opposite sides?
H and Cl, that is a very good question. So what's gonna happen is that you would have the Cl and this methyl group switch position. Therefore, if they do a rotation, your Cl is gonna be on the front and that methyl is gonna be in the back.
So if we were to rotate, the Cl would come out in the wedge, which is not opposite.
The Cl would come out to the wedge and your H would, if we just rotate half of the molecule, right? Because they're independent bonds and one side can rotate, the other one can stay the same. So if those two rotate, your Cl would come out on the wedge and your methyl would go back into the board in dashes. And if your H and Cl, if your H is going back, your Cl is going out. If you look down at the molecule, they're actually in the same plane and opposite directions. Just imagine, right now we're looking at the molecule from the side. We're looking at this ring and those things. But can you see my cursor?
Yeah.
Okay, imagine looking at the molecule from here on top. So you won't be able to see. It's just like looking at, it's almost like when you try to draw a Newman projection. So when you look down, this bond is gonna turn to the left or right.
Oh, you're asking me?
Yes. So the wedged bond here on this carbon, which is your beta carbon, do you think it's gonna be on the left or gonna be on the right? If you look down.
Maybe. I'm not sure. I think it'd just be a guess if I say an answer right now. Like looking down, like I would just see the wedge pointing to me, but I don't know how it would look like direction-wise.
Right. Okay. So remember that the wedge, right now we're looking at the molecule from the side, therefore the wedge is pointing at you.
Yeah.
However, if we look from the top, the wedge is no longer going to be pointing at you. The wedge is going to the wedge is going to stay in the plane of your computer screen. Or just imagine taking this molecule in your hand and rotate it 90 degrees counterclockwise.
Like to the right?
Like to the right, you're absolutely right. Just imagine taking this and turn it 90 degrees to the right.
Yeah, and then where would it end up? Like,
Then where would your H end up? Is it gonna coming out, go in the plane of the board, or?
oh, well, the H would just come out to me now. Like, would it go to a wedge?
The H would, if you rotate it 90 degrees, the H would be in the plane of the board.
Oh, no. Yeah, you're right, because it was already pointing into the board. Okay.
Yeah, it's pointing in, it has to be in the plane, and then it can point at you.
Yeah, exactly. Okay, that makes sense.
Right, cool. So if you rotate it 90 degrees, your H is going to be in the plane of the board.
Mm-hmm.
All right. So if you rotate 90 degrees, where is that chlorine going to be right now?
It would be a wedge, right?
To the right.
Yeah, right, wedge. Yeah, that's what I'm thinking.
It would be a wedge?
Like, well, if we're rotating the whole molecule 90 degrees?
Mm-hmm.
Oh,
180 degrees would be in the wedge.
no, wait, hold up. Wait, no, not a wedge. No, sorry. No,
In
wait.
the plane of the board, right?
Exactly, yeah. So then
It'll be in the plane of the board. Therefore, this H and that Cl would be in the same plane, but still cis to each other.
yeah, it'd still be
So
cis.
that's not good, because E2 cannot happen when the leaving group and the H are cis to each other.
Oh, well then, no, if you turn it 90, would it also be like in plane?
Yeah, they're in the same plane, yes.
Yeah, so then it would be on the plane of the board.
They would be in the plane of the board together.
Mm-hmm.
So we don't have a problem with that. What we have the problem with is that they're cis to each other. So to solve that problem, you just swap the methyl and the chlorine on the alpha carbon.
Okay.
That way your H and your Cl are going to still be in the same plane, but they're trans to each other.
Okay.
Cool. All right. Any other questions regarding what we discussed today? If not, I'm going to stay after the lecture in case you have questions that you want to ask me privately. It could be for this lecture or for past lectures. I don't really care. Anyway, so that's the end of my lecture. People can feel free to leave. I'm going to stop sharing my screen. And feel free to stay if you want to.